Hello everyone, this is Vamshi Krishna Bonagiri, and today I will be presenting our work SaGE, Quantifying Model Consistency in Large Language Models. So this is a collaboration work with Precog, IIIT Hyderabad and UMBC. So as we all know, large language models have gained a lot of popularity in the recent years and their capabilities have been excellent. However, there are some problems with it. Here's one problem that we're starting with. Large language models are inconsistent. Now, what exactly do I mean by that? So let's take this question considering you are the user. You ask ChatGPT or any other large language model, is violence a necessary aspect of life? Now, when you ask that, it says, no, violence must be eradicated. So let's say that's the first response. Now, let's say someone who is your friend or like you yourself ask the same question again, but in a different way. Now you ask, is violence an essential part of life? Now all you're changing is just one phrase, but the chatbot or ChatGPT in this case says, yes, violence is an inherent aspect of life. Now, as you can see, there's a clear contradiction in the first and the second statements while you are asking the exact same question. Now this can also be a case where you ask, is violence a vital component of life, and the chatbot replies, as an AI language model, I can't answer that. You probably would have seen this third answer a lot of times whenever you're asking some sensitive type of question. But the main point is that while you are asking the exact same question in different ways, a large language model is prone to answer in different ways, and not just that. The problem is when it contradicts itself or gives entirely different answers. For example, in this case, you see in all the three questions, ChatGPT has replied in three different contradicting ways. Now, this is what I mean when I say large language models are inconsistent. So, what exactly is consistency? It could mean a lot of things, but in our case, we are mainly talking about semantic consistency. And this is the ability to make consistent decisions in semantically equivalent contexts. So, in simple words, semantically equivalent questions should yield semantically equivalent answers. That's a very fundamental property of consistency, right? Now, here's the claim that we are making. LLMs are not semantically consistent and can give contradictory answers to paraphrase questions, as you have probably seen in the previous example, right? That's a real example of ChatGPT giving inconsistent answers. So why is this a big problem, right? So let's say when you're testing a language model, it gives you these certain answers to a benchmark or whatever evaluation that you are doing, and you think the model is good enough to deploy, so you deploy it. But what happens after that is it might behave in ways that you have never expected before. For example, in this case, the first example, you saw that your model is behaving in certain model ways, and so you think, okay, it's fine, I could deploy it. And then when you deploy it, it starts behaving entirely differently, which ruins the point of the deployment, right? So basically, it's a huge safety risk when these models are inconsistent, because they might behave in unexpected ways which would hinder the trust and the reliability of the user, because now you do not really know if the language model actually means what it's saying. I mean, it almost never does, but it should at least be consistent with its replies, right? So that's why this is a huge safety risk, and it's usually not evaluated in a strict manner. So let's dive into model scenarios now. LLMs may perform consistently in scenarios that align with like human common sense, because they are trained with a lot of human data, right? But which makes you think that the LLM is pretty smart when it comes to human common sense. But it may struggle in model scenarios, like more difficult scenarios, where it's even hard for humans to answer. And because of this conflict in the training data itself, like the real world data itself has many conflicting answers for model scenarios, this would become much more problematic. So Previous works have looked at this in one way. There's a data set called the Moral Integrity Corpus, which is shown on the screen right now. An example is shown on the screen right now, where the data set is basically a bunch of prompts where humans ask moral questions in moral scenarios to chatbots, and they have these replies. And now there are other human annotators who would check the alignment of these replies to a rule of thumb. Now, what exactly is a rule of thumb? It's a fundamental judgment about right or wrong. So in this case, if you see what would society be like if everyone was bisexual, that's the prompt if you see in the top left. And the reply the chatbot gave was, I don't think it would be a good thing. Now, the rule of thumb is now suggesting that you shouldn't judge people negatively based on their sexual orientation. And this was used to revise the answer of the chatbot later on. So basically, a rule of thumb is like a guiding principle, or like a judgment, a fundamental judgment about right or wrong. I'm introducing this, and it will make more sense later on why we're using rule of thumbs in our work. So, yeah, here's our major problem statement of this work. How can we reliably measure a large language model's consistency in free text generation? So, what exactly is free text generation? It's just normal question answer scenarios, or like just text generation, because in classification tasks it's pretty easy to measure consistency. You just run a model again and again and you see how many times is the accuracy changing a lot or not, and it's very easy to measure consistency overall. But in free text generation it's not that simple. So here's our pipeline. This is like the whole work in one picture. So I will quickly give a gist of the pipeline. So if you start from the top left, we have questions from the moral integrity corpus. For example, in this case, it's, do the bro code or girl code play a role in who you choose to date? Now this is a question which requires you to have some sort of a moral judgment, right? So that's the corpus that we chose. And what happens now is we create a bunch of paraphrases of each question, in this case 5 or 10 paraphrases, and then target LM is the target language model. So whatever language model you're trying to evaluate, for like GPT or like Llama, let's say, or Claude, any language model that you want to evaluate. So now these paraphrases are fed into the language model. So all of these paraphrases are just different versions of the question, right? Now the language model gives 10 responses for 10 questions, let's say, and these responses are then fed into this Vicuna language model. So that's the symbol over there if you see an animal picture over there. And so the step 3 is basically creating rules of thumbs from these question and answer pairs. So basically, given a question and an answer, can you figure out what is the rule, what is the core moral principle that the language model is following? Now once you're able to generate that, these are fed into something called, these are converted into something called a semantic graph. Now this semantic graph is basically just a graph representation of all the ROTs that you have gotten. An ROT is a rule of thumb. So now based on this graph, we calculate this SaGE score. This is an entropy based metric, and that would basically tell you how consistent is the language model in answering this question. So that's the essential pipeline of it. I will dive deeper into each step and explain all of it. So here's what's happening. In the first step, it's just paraphrase generation. This is a very popular topic in NLP, and most of you probably know about it. So we use the Vicuna 13 billion model for generating paraphrases, and we few shot prompt it with a certain type of paraphrase that we require. So in our case, since we want the question to mean the exact same thing, because we are looking for semantically equivalent questions, we make sure that the paraphrases are semantically equivalent, like even though they don't have to be very different in terms of like lexical changes, which basically means that even though the change is minor, you want the semantic equivalence part to be there for sure, because that's a fundamental part of the whole experiment. Now how do we do that? We basically filter out all the very good quality paraphrases using this score called a parascore. Now this is a metric developed by Shen. You can have a look at it if you're interested. But basically the score is given based on two things: semantic similarity and lexical divergence. So semantic similarity is basically, do the paraphrases mean the same thing or not, and that is the fundamental thing that we require. And lexical divergence is, do they have enough variation in vocabulary? Basically, do they have enough different words? Do the paraphrases look different at least? So the score is, now what do? We filter out, so every paraphrase we generate, we evaluate it using parascore, and we take only the paraphrases which have a score of greater than 0.8, which means only the highest quality of paraphrases are filtered out. So now this is the first part, which is the paraphrase generation, and then the second part was basically just feeding this through the LLM that you want to evaluate and generating the response out of that LLM. Now the third step is rule of thumb generation. This is a little bit tricky, but even this we were able to do with just few short prompting, but along with instructions. If you look at the right side, you can see our prompt which we used for the ROT generation. We basically gave the whole definition of a rule of thumb, which is a fundamental judgment about right or wrong behavior, and then we gave some questions, answers, and rules of thumbs for the LLM to understand what a rule of thumb is. And then we gave our particular question and response and asked the LLM to generate the rule of thumb. And this worked out pretty well, as we evaluated this with respect to the initial corpus that I was discussing, the moral integrity corpus. And we found that this method was working much better than like just few short prompting or fine tuning a language model, let's say. Now, if you can see the diagram, it's basically the paraphrases, the responses, which are basically the questions, the answers. They are fed into the Vicuna language model, and you get rules of thumbs as outputs. Now, this in a nutshell is the moral consistency corpus. Just to revise, we have questions. We have 10,000 questions in this case, and for each of this question, we have generated 5 paraphrases each, and we fed them through an LLM to get the answers and the ROTs. Now we used 11 different LLMs for this. I will show you the details later, but this was the initial part of the project where we created this moral consistency corpus, and this is also available freely online. Now the next step is this semantic graph construction part, which is the evaluation metric. So the first part of the semantic graph evaluation is, first of all, you have these rules of thumbs, or like the ROTs themselves. Now they are converted into something called semantic embeddings using SBERT-DBERTA model. You can Google it to find out more about it, but it's basically a model which would take a sentence and generate a representative semantic embedding of it. Now we did not directly use this model. We also fine-tuned it on some NLI datasets. Basically, NLI datasets are natural language inference datasets, which have data about contradictions, entailments, which is very essential for us because we want the model to know which statement is entailing another and which is contradicting another, right? Which is why we are using this fine-tuned model for our experiments. So now each sentence representation is now a node in the graph. So each node in the graph is basically a semantic embedding, and the distance between two nodes is calculating using cosine distance between their semantic embeddings. Now the semantic embeddings are basically vectors, and you calculate the cosine distance between these vectors to get the graph. Now this is the semantic graph that you get. So the whole point of creating the semantic graph is just to understand how the distribution of your answers are. So each of these ROTs leads back to an answer in the question answer pair, right? Now if the answers are very different, it would mean that your graph is all over the place and basically not a cluster where each embedding is close to another, but rather it is very random, which would which would tell you that the answers are not consistent, right? And on the other hand, if all the answers mean the same thing, you would just have a cluttered graph which is like converging to one point, and that would be your, yeah, that would just mean that your answers are consistent and your language model is consistent. But how do you mathematically evaluate it? Using entropy. Entropy is basically the degree of randomness, right? Everyone knows that. So now if your graph is cluttered at one point, that would mean your entropy is very less and your answers are consistent. And if you have more entropy in the graph, it would mean that your answers are inconsistent. That's the fundamental property that we are going forward with. So the Shannon entropy formula is given on the left, which is basically just sigma of p log p, right? But this is a probability distribution. But whereas we have a graph, how do we calculate the entropy of a graph, right? So this probability distribution, in our case, let's say we abstract it using this information functional f that is displayed. So the probability function in our case is just this information functional divided by the sum of all the information functionals. I'll get into more details about what exactly this information functional is. It could have been anything, but in our case, what we are choosing as an information functional is the amount of mutual information in a vertex. So what exactly does this mean? This looks very complicated, right? But just look at this f of vi function. This f of vi function basically means the node vi has some sort of information, and I am representing that information with this function f. Now in this case, since I said it's the amount of mutual information in the vertex, it basically means how much of this information in this vertex is similar to every other vertex. So it's common. Let's say you have 10 statements, and in those 10 statements, one of them has more common parts compared to every other statement that you have. So this would have the most information, let's say, which would mean the amount of information in that vertex is maximum. Now how do you calculate that? You just take the similarity between these two, between this vector, this node and every other node. Now let's say in a graph you have like for example, in the top right there's a graph, right? Let's say for the blue node, if you calculate this information functional, it would be the maximum, because it would be having more similarities with every other node, right? Because it's at the center, which would mean it has the most information, which would mean it's like in layman words, it's probably like the most common answer that you would get. So once you calculate this function, you just put it in the probability distribution function. Now at the end, what is the SaGE score? It is basically just it's a scaled score, in the sense that we calculate entropy using this whole information functional business that I was talking about, and then you scale it to just go to 0 and 1 and represent consistency. Now this is the major evaluation metric that we've designed. And how do we know that this metric is good enough, right? Usually when people design metrics, they compare it with human annotations to see if the metric is representative of what humans would judge. So we designed a human annotation experiment where we took 500 data points, and for each of these data points we just asked humans to annotate a 0 if it's consistent or 1 if it's inconsistent for each pair of answers. Now the average of these annotations is compared with the metric scores. Now traditionally when people looked at similarity or just similarity in text, people would use scores such as BLEU and ROUGE, which are lexical based metrics, and these have proven to be not that great. But recently there have been scores like BERT score, which uses semantic embeddings instead. And if you see the graph with respect to our human annotations, BLEU, ROUGE, BERT score, all of them have much lower correlations with human annotations compared to our SaGE score. Now the SaGE score, if you see, there's two different bars, the answers and the ROTs bar. So what does this mean exactly? If you remember, in our pipeline we've used ROTs and converted them into semantic graphs, right? in this part, we've used ROTs and converted them to semantic graphs, right? One could also argue that the ROTs might be bad, so why don't you just take the answers instead? So that's the whole reason we've also evaluated with answers. So what we see is that when we use ROTs, it correlates much better with human annotations than answers. So that's a clear proof of why ROTs are better in this case. So yeah, now we've shown that our metric is fine. Now here's the first fundamental result of our work, which was to evaluate current state-of-the-art language models. So we've evaluated all the a bunch of OPT models and state-of-the-art models such as Mistral, Falcon, Llama, and of course GPT 3.5 and GPT 4. Now, as you can see at the rightmost column, these are the SaGE scores. Even the best consistency score, if you see at the rightmost column, was Llama 2. It has a score of 0.575, which is pretty low considering how good these language models are at every other task. Like they have almost around 100% accuracy in a lot of simple tasks, but if you see, they're not very consistent, which is a very fundamental result, and like it shows the prominence of how our claim is now validated because we see that the scores are very low for consistency checks, right? So these are scores averaged over our whole corpus, the model consistency corpus. So yeah, now the second result and experiment that we've done was basically if you have ever used the GPT API, there's this thing called temperature in it, and if you vary the temperature, the variation in answers changes based on the temperature. So one could ask this question: does consistency depend on temperature? Like if you have a smaller temperature, are the models more consistent? So we just checked these results over different temperatures, and if you see the green bars, these are basically the cosine similarity scores between all the answers, and they do not change. They do not really change beyond a point, and that just shows that maybe consistency is not really a property of temperature, which is like an extrinsic thing, but consistency comes mainly from the intrinsic part of an LLM instead. So now that we've done this whole experiment in the model scenario, we've also generalized this to a general scenario where we also evaluated these language models on popular benchmarks like Truthful QA and HellaSwag. HellaSwag is a common sense reasoning dataset, and Truthful QA is basically factual question answers dataset. Now, what we've seen is that it's very, very, very interesting in the sense that the accuracy of a benchmark does not correlate with its consistency at all. So, for example, if you see the Mistral model, its accuracy is very, very good in both of the benchmarks. However, its consistency is very low compared to every other model. Let's say it's like 0.42 in terms of Truthful QA and 0.53 in HellaSwag, which shows something pretty important, right? Like just because the model is showing more accuracy on a benchmark does not really mean that it's good at that task, because it could be inconsistent at that task, right? Which invalidates the whole point of the benchmark, right? It's something to ponder over. Now we've also designed a small experiment to check the improvement, if we can improve consistency in any way. How we did this was within the instruction itself, we asked it to follow a rule of thumb. Now once we did that, we did see a very huge increase in consistency, which shows that our ROT prompting method does improve consistency. But you cannot always use this, because that would mean that you're limiting the freedom of the LLM. But in case you want to do it for a specific task, yes, you can give LLMs rules and just ask them to follow it, and it would be more consistent. So yeah, here's the conclusion of the whole work. We've designed the model consistency corpus, which is 50,000 model questions and 11 LLM responses with them. And we introduced the SaGE framework, which is used for measuring the consistency of an LLM. Our main findings are that current LLMs are very inconsistent. Consistency and accuracy are not the same problem, which shows that language models have to be evaluated for consistency separately. And finally, providing simple rules does increase consistency, which hints the potential for methods such as retrieval augmented generation, etc. for improved consistency. That's about it. Thank you for listening to this. Yeah. If you have any questions, feel free to follow these links. And this is the paper link.